Okay, so here's the part two of the week for audio notes. So we are going to talk about the bulk deformation process in the metalworking, and in this slide, I'm going to actually the process is going to be divided into a shorter slides, so you don't feel boring. So I'll start with the bulk deformation in general. As we mentioned, it's going to be a metal forming operation which cause a significant shape change by the deforming of the metal parts whose initial form is bulk rather than a sheet. So in bulk deformation, this initial form was bulk rather than sheet, and we're going to cause a significant shape change to it. The starting forms can be cylindrical bars and pellets, and can be rectangular pellets, can be slabs and similar shapes. And these processes suppress the metal sufficiently to cause the plastic flow into the desired shape, performed as a cold or warm or hot working. The importance of the bulk deformations are in the hot working, we can achieve a higher significant shape change to be accomplished. And this mainly because, as we mentioned earlier, we're going to reduce the flow stress of the material and increase its ductility. In the cold working, we're going to have high strength during the shape change due to the strain hardening. Usually in the case of the bulk deformation, we're going to have little or no waste. In some operation, there are going to be a near net shape or net shape processes. The part will require little or no subsequent machining in that case. The four basic bulk deformation processes are going to be the rolling. We're going to have a slab or a plate. It's going to be squeezed between the opposing rolls. You saw that in the lab. The second one is going to be the forging, where the work is going to be squeezed and shaped between two opposing dies. The extrusion, where the work is going to be squeezed through a die opening and thereby going to be taking the shape of that opening. Finally, we have the wire and the bar drawings, where the diameter of the wire or the bar is going to be reduced by pulling it through a die opening, or actually multiple dies opening. So we start on this sheet with the rolling. It's going to be quite long. And to achieve the deformation in the rolling, the work thickness is going to be reduced by the compressive forces exerted by the two opposing rollers, as you can see in this photo. The rolls are going to be rotating rolls, perform two main functions. The first one is going to be pull the work into the gap between them by the friction between the work part and the rolls. At the same time, it's going to be squeeze the work to reduce its cross section. We can have different shapes to be made by the rolling process. Like I can take the bloom and change it to the structural shape or the well shape. I can have a slab, then I'm going to simply roll it to make a plates or sheets, or I can make a coils. I can have a square pellets, and then I can change it into bars or rods. We have different types of the rolling. We can have it can be classified first based on the work geometry, which is going to be a flat rolling, which is going to be used to reduce the thickness of the rectangular cross section and make it just thinner. That's it. Okay. The other type is going to be shape rolling, where a square cross section is going to be formed into shapes like the I-beam. Also can be classified according to the work temperature. So I can have the hot rolling, which can achieve a significant deformation. And we have the cold working, which will produce sheets and the plate stock. So in the case of the side flat rolling, we can see here the side view of the flat rolling. And you can see that we are simply going to be indicating many of the parameters that's going to be used later to do some calculations. We can have the thicknesses, the initial thickness and the final thickness. We have the velocity, we have the roll velocities, we have the angle theta, and we have the roll radius. So the draft is going to be the amount of the thickness reduction. So D is equal to the TL, or the initial thickness, minus the final thickness. The reduction is going to be draft expressed as a function of the starting stock thickness. So it's going to be equal to the D value, or the draft value, divided by the initial thickness. Okay, so these are two equations to calculate the draft and the reduction. Actually, there are more calculations to calculate the power and the force required to do the work, and this should be done by the calculation of the flow stress, and then we can go with the things. I will show you that in the example. The shape rolling, opposite to the flat rolling, is going to be doing a different shapes from the part. So it's going to be used to produce a construction shapes like the I-beams, the L-beams, and the U-channels, and also the rails for the railroad tracks, and the round and the square bars and roads. The work is going to be deformed into a contoured cross sections rather than a flat rectangular shape. Can be accomplished simply by passing the work through rolls that have the reverse of the desired shape. The rolling mills, which are an equipment in massive and expensive properties. The configuration we can have for the rolling mills are going to be, we can have the two heights. The first image is the two heights. Okay, where we're going to have two opposing rolls used for the long products like the sections. We can have the second part is going to be used for the light sections and the bars. We're going to have the three heights, height 1, 2, and 3. Work passes through the rolls in both directions. So we're going to get first and then get second stage, and we're going to reduce the thickness in two stages. We can have the four heights, or the like this one. Okay, the four high, which we're going to have two work stand with the steel supported by the backing rolls supports the smaller rollers, and this will giving a greater accuracy for the rolling of the flat products such as the plates, because it's going to work like a gear. Okay, we're going to require to have less torque here, and thus is going to give us something like the ratio of the movement. We can have the cluster type. Okay, which is going to be multiple backing rolls on the smaller rolls. And we can have the tandem rolling mills, which is going to be a multiple stage of the two high system, but it's going to be reducing the gap between them every time. If you are going to visit the Kampla steelwork, you'll find something similar to that. So the metal is going to be first milled, and there's going to be casted, and we're going to be simply run between the roller to control. You can see the rollers here, okay, to control what will be the size of the ingot we're going to achieve at the end. Okay, so there will be the end of the part 2. We're going to move to the part 3 next.